4 astronauts have just spent 7 days farther from Earth than any human being has traveled in over 50 years. They've looped around the moon. They've looked out the window at a surface no one has stood on since 1972. They're healthy. The spacecraft is functioning. Mission Control is calling it a success. And then comes the part that has killed people before: re-entry. The moment Orion hits the atmosphere at nearly 40,000 kilometers per hour and the crew has to trust that a heat shield, one that has never carried humans before at this speed, will hold between them and temperatures that exceed the surface of the sun. That's not a metaphor. That's the physics of what happens when you try to land after going to the moon. Artemis II is NASA's first crewed mission under the Artemis program. It's scheduled to carry 4 astronauts: Reed Wiseman, Victor Glover, Christina Koch, and Canadian Space Agency astronaut Jeremy Hansen on a free return trajectory around the moon. No lunar landing, no orbit insertion. The goal is to prove the system works with people inside it. And, by most measures, the mission profile looks manageable. A well-tested rocket. A spacecraft that already flew uncrewed on Artemis I in 2022. A flight path that has a long heritage going back to Apollo. But the flight path coming back? That's a different conversation entirely. Here's what people sometimes get wrong about spaceflight danger. They imagine the risky parts are the dramatic ones: the launch, the vacuum of space, the moon itself. And those things do carry risk. But the launch phase, as terrifying as it looks, lasts about 8.5 minutes. If something goes wrong, abort systems are designed to pull the crew capsule away from the rocket. Space itself is silent and cold and unforgiving. But Orion is a sealed environment, and the threats there are slow and manageable: radiation exposure, microgravity effects, equipment monitoring. The moon flyby is essentially passive. The crew isn't landing. They're not firing engines to enter lunar orbit. The spacecraft follows a natural arc around the moon and uses gravity itself to slingshot back toward Earth. None of that is trivial, but none of it involves the fundamental, physics-dictated violence of what happens during re-entry. When Orion returns from the moon, it isn't just falling. It's moving at roughly 11 kilometers per second relative to Earth, what engineers call lunar return velocity. That's about 39,000 kilometers per hour. For comparison, the International Space Station orbits at roughly 28,000 kilometers per hour. The space shuttle re-entered at similar speeds. But Artemis is coming from the moon, not from low Earth orbit. It's carrying more kinetic energy, and all of that energy has to go somewhere. The answer is heat. An enormous, almost incomprehensible amount of heat. When the capsule hits the upper atmosphere, the air in front of it can't get out of the way fast enough. It compresses. That compression generates temperatures that NASA measures at approximately 5,000 degrees Fahrenheit at the surface of the heat shield. That's not the air temperature around the capsule. That's the temperature of the plasma being created at the shield's surface. The surface of the Sun is roughly 10,000 degrees Fahrenheit. During peak heating, Orion's heat shield is operating at roughly half that. The Orion heat shield is the largest of its kind ever built. It's nearly 5 meters across, and it's made of a material called AVCO8, an ablative compound that works by slowly burning away. As the outer layer ablates, it carries heat with it, protecting the structure underneath. This is not a new idea. Apollo used ablative heat shields. But Orion is heavier than the Apollo capsule, and it's coming in faster, because the moon is farther away than the space station, and the physics of that distance accumulates into velocity. Artemis I gave engineers the data they needed to know the heat shield could survive this. But during post-mission analysis, NASA found something unexpected. The heat shield had ablated unevenly. Chunks of material had come off in a pattern engineers hadn't predicted. The structural integrity held. Orion landed safely in the Pacific Ocean, but the behavior wasn't what the models had expected. NASA spent months analyzing this anomaly before certifying the vehicle for crewed flight. The conclusion they reached was that the ablation pattern was caused by a phenomenon called late boundary layer transition. Essentially, the flow of plasma around the capsule became turbulent in a way that stressed certain areas of the shield more than others. This is real, documented, and the reason the re-entry environment remains the most technically uncertain phase of the entire mission. Think about that for a moment. An uncrewed test flight flew perfectly by every measure that counted, and it still produced an anomaly that required a year of investigation before humans could be put inside the vehicle. Now imagine being one of those 4 astronauts during re-entry. You're strapped into your seat, you cannot see the heat shield, it's on the bottom of the capsule, and you're inside. What you can see if you look through the window is plasma, orange and white light wrapping around the capsule. You're in communication blackout because the plasma sheaths the capsule in ionized gas that radio signals can't penetrate. Mission control cannot reach you. You cannot reach them. For approximately 3 to 4 minutes, you and your crew are entirely alone, traveling at hypersonic speed, betting your lives on a material burning away at temperatures half the surface of the sun. There is also the question of G-forces. During a standard re-entry from low Earth orbit, astronauts experience roughly 1.5 to 2 Gs of deceleration. During Artemis II re-entry, peak deceleration is expected to reach approximately 4 G acceleration. That's 4 times your body weight, pressing down on you continuously for several minutes, while you're monitoring systems, while you cannot communicate with the ground, while plasma lights up the windows. And here's something that makes Artemis specifically more complex than Apollo. Orion uses what's called a skip re-entry technique. Rather than plunging straight into the atmosphere, the capsule enters, partially exits the atmosphere again like a stone skipping off water, and then comes back in for a final descent. This technique gives mission planners more precision in where the capsule lands. It reduces the splashdown zone from a circle hundreds of kilometers across to something far more manageable. That matters for recovery operations. But it means the re-entry isn't a single event. It's 2 heating events, with a brief respite in between, before the final parachute sequence begins. The parachutes are their own engineering achievement, and their own potential failure point. Orion deploys 2 small drogue chutes to stabilize the capsule, then 3 main parachutes, each roughly 35 meters across. They're packed into a space about the size of a small closet. They have to deploy in sequence, at the right altitude, in the right order. The whole sequence takes several minutes. If one fails, the backup systems are designed to compensate. But there is no backup for the heat shield. There is no abort option during peak heating. The capsule is committed the moment it hits the atmosphere. Some researchers have pointed to long-term questions about heat shield behavior that still aren't fully resolved. The ablation modeling for lunar return velocities has more uncertainty baked into it than modeling for lower speed re-entries, simply because there's been less flight data at this speed. Apollo flew 6 successful lunar landings and provided data. But Apollo's command module was smaller, lighter, and the fleet of missions still represents a limited dataset at the edge of what material science had to handle. Artemis is a different vehicle in a different era with different materials. The Artemis I data is invaluable, and it also revealed that the models weren't perfect. NASA's engineers are not hiding this. They've published the analysis. They adjusted the flight trajectory for Artemis II to reduce peak heating loads based on what they learned. But adjusted is not the same as solved. Most of the aerospace engineering community is confident the fix is adequate. The trajectory modifications reduce peak heat flux. The anomaly, while unexpected, didn't threaten vehicle integrity. And NASA has a deep institutional habit of rigor about exactly these kinds of questions. But there's a difference between confident and certain. And during those minutes of blackout, with 4 people inside that capsule, the gap between those 2 words is where all the tension lives. When the parachutes deploy and Orion descends toward the Pacific, when the recovery team can see it on radar, when the capsule hits the water and the crew radios mission control that they're okay, that's not just a mission milestone. That's the closure of the most dangerous chapter of the entire journey, not the launch, not the moon. The return. There's a reason the Apollo astronauts talked about re-entry as a separate psychological experience from the rest of the mission. They knew the physics. They understood that what the atmosphere was doing to their spacecraft was not just fast. It was violent in a way that no other phase of flight was. The moon was silent and still and remote. Re-entry was all fire and G-forces and radio silence, and nothing to do but wait. Artemis II is a test. A human-rated test of a system designed to eventually carry people back from the lunar surface, over and over again. Getting that re-entry right, understanding exactly how the heat shield behaves with this capsule, at this speed, with this trajectory, is not a footnote in the mission. It is the mission's most fundamental question. Whatever else happens on that flight, that's what the engineers will be watching for when Orion breaks through the clouds.